Hey everyone, let me just admit everybody to the class. How you guys doing?
Doing well.
Good, good. Let's give it a minute for everybody else to join up. Is everybody able to find the table A online on our Blackboard page? It's also, we
Yeah,
have a copy,
I got it.
we have a copy like this in our book too, by the way. I'm sorry, go ahead.
I got it from the page.
Yeah, okay, good. Good. You guys are gonna need it, I think, for the tests and certainly for the homeworks and stuff too. So go ahead and print out a copy of that so that you can have it for the rest of the semester. Just some administrative stuff while everybody's still joining the class. Our homework is due tonight. This will be 4.2. We're going to have, this is a carryover from last week because I didn't collect it last week. 4.2, 4.3, and 5.2. 5.3, I know I put on the assignment originally. We won't make that due tonight because we most likely won't get through 5.3 today. Also, 5.3 will not be on the exam today. Just to let you know so that you can focus your attention on other things. The material from the last exam, right? So everything from 3.5 up to 5.2 will be included in the exam. So it's not cumulative for the whole semester, just the stuff from the last exam. Okay, so kind of think about that. What I'd like to do today is continue going through 5.2. I want to take a step back and think about some of the examples that we did yesterday, go through more examples, make sure that we've got the topic covered, and that'll be it for the exam. And then I want to actually make a start on chapter 5.3, even though that will not be on the exam, because we have a schedule and we need to make sure that we stay on our schedule, and then we'll be able to pick up probably the rest of 5.3 next week. If you guys have questions about stuff, I have office hours today at 12:30 to 1:15. If we have time at the end of class, I can answer some questions about the homework as well, if you want to ask any questions about that. Also up online, I put up a new folder for exam 2 review material. This is a review like from previous semesters where we group things differently. And so there are some things on there that you might want to take a look at. A lot of the stuff from the exam 1 review, we're going to carry over. Like you can be able to see, hang on a second. You'll be able to see the other questions on exam 1 review. Those are pertinent to now. And then examples, questions, I think 1 through 4, I said, although looks like question 3 is an unbiased estimator. You guys don't have to worry about that at this point. We'll talk about that later. That won't be on the exam, the unbiased part, but the estimator part certainly will, because that's chapter 5.2. Let's see, what else? Yeah, so keep that in mind. The test will be like the other tests where the test becomes available at 4 o'clock today, and then it's going to continue to be available until 4 o'clock tomorrow. It's going to take the whole class period, okay? So make sure that when you start it, you give yourself enough time to actually finish it. And then you'll be able to upload your work like you have done in the past. You take your work, scan it in, upload it into the separate column for the exam 2 work. Okay, I'll put all those columns up online. You'll be able to see them later today. Okay, I think with that said, let's go back to chapter 5.2, which is our estimator. So we're talking about this chapter 5.2 is about the method of maximum likelihood estimation. And why do we care about that? What do we want to do? So the whole point when we start to do statistics is to be able to compare our sample set to like a mean, like a population mean. And we want to be able to make inferences about what's the population doing based on what we're seeing. Sometimes we have population data, sometimes we don't. Sometimes we just have data from our sample set. And so we need to be able to extrapolate based on our sample set. What's the estimator, like what's the mean or what's the variance, say for this, sample data that we're looking at. And so we need methods, right? We need some tools to be able to help us think about how we're gonna take a look at the mean. If we don't know what the population mean is, we need an estimate for the population mean so that I can run some statistics on the sample data that we're getting. Yesterday, we went through example 2, which I've got up on the screen here. Example 2, I just want to comment on because we're going to do example 3 is with the continuous distribution. So example 2 was we said it was independent Bernoulli random variables. Bernoulli random variables means that it's a binomial experiment, right? So that means that in the background, the data themselves are yes, no answers, okay? So that there's only one of two binomial, there's only one of two possible answers that we can have. We often assign these, we think of, the book talks about these, and sort of theoretically, we think of a yes answer as being a success, a no answer as being a failure. And then it doesn't mean like, oh, yay, we succeeded, or oh, no, we failed. It just means that it satisfied the hypothesis that we had going into it. Does the person own a sports car? Yes, that's a success because they do own the sports car. We want to be able to make some kind of an inference about sports cars. That's example 2. So one of the things that we did for here was we taking a look at example 2, and I'm belaboring this point because there are a couple important things that we need to think about when we're doing this. So example 2 is essentially a discrete, right? Because I've got it's a Bernoulli experiment in the background, binomial experiment. And so we're looking at our likelihood function, right? We're deriving it. We've come up with, you know, the probability of success, the probability of failure, you know, raised to the number of successes, raised to the failure. Is it a 1 or 0? And so we're gonna, these are independent, so I can multiply all these probabilities out together and come up with my likelihood function. The likelihood function is a function that's going to give us an estimate for what is our P, what's our maximum likelihood estimator for P, which is our probability of success. Okay, so I need to be able to have an estimator for the probability of success. I want to call your attention to all the work we did. There's a lot of like algebra and calculus involved. We took the you know, natural log, so we can, you know, simplify this equation out. It doesn't look like we simplified it, but we did. And then we took the derivative, set it equal to 0. We're trying to find the maximum, right? So we take the derivative, set it equal to 0, and then we solve for P. P is the thing we're looking for. That's our proportion. P stands for proportion, also probability of success. But it's essentially our proportion of successes to the total samples that we went out to find, right? So if we have n, let's see, let me get this down here. So if we have n total samples, right, and then x sub I, right, x sub I is either a 1 or a 0. So when I sum all these up, when I sum up all the ones, it's going to give me the total number of successes, essentially, out of the total number of samples. So our P value, our P hat, or our P sub E, which is our estimator for our proportion P, is essentially the total number of successes out of the total sample size. I'm calling your attention to that because, and I'm going to write this down in here too. So for a binomial experiment, right? This is our binomial experiment. I'll write it down over here. Our binomial experiment, right? Our P hat is essentially the average, right? Where it's the proportion, right, of number of successes out of the total samples that we have. So this is number of successes out of the total number. Oops. Total number in our sample, right? So say if we have a sample of, you know, 500 people that were polling for something and 350 of them said yes, okay, my P hat, my maximum likelihood estimator for that probability of success is going to be 350 out of 500. Okay, that's what we have here. We've summed up all of our x sub i's, which x sub I equals 1 if it's success. We're summing all those up, and this n is our total sample size. So I'm calling your attention to that. This is for our binomial experiment. We're going to see when we do this, our next example, example 3, we're taking a look, is a continuous random variable set. Okay, and then we're going to be able to make an extrapolation out of what is our, we're going to be looking for mu, right, and a maximum likelihood estimator for our mean. Okay, so when we go to do that, let's take a look at example 3. When we go to do that, example 3, we're going to take a step back when we're all done with example 3 and then extrapolate what we're looking at in terms of, you know, things that are normally distributed. Okay, so I'm on my lecture note examples for chapter 5.2, and example 3 is the one that I'm looking at. Okay, so example 3 says, suppose the weights of randomly selected American women are normally distributed with an unknown mean. Okay, this is the problem. So it's an unknown mean. We need to be able to come up with a maximum likelihood estimator for our mean, right? And we've got some kind of standard deviation sigma. Okay, so maybe we're given that. this is a little academic, right? Because if I know what the standard deviation is, I probably know what the mean is, but we're working with the problem here. So we have a random sample of 10 American women, and they have the following weight results. Okay, so here are the weights that of these 10 American women. So what we want to find is, given the sample size, what's the maximum likelihood estimate of our mean value? Okay, so this is going to help us come up with an estimate for our essentially our mean. All right, so let's see. We're going to assume, like all this stuff, we're going to assume that we're, so we're told that it's normally distributed, which means that I'm going to use, let's write this down. So if it's normally distributed, which is a safe bet, because most data, unless you're told otherwise, most data sifts into a normal distribution, normally distributed, which means that I'm dealing with basically a PDF that looks like, right? I've got my samples, right? For each individual sample, right? I've got a mean and a variance, and this is going to look like 1 over sigma 2 pi, pi is inside the radical, and this is times e to the minus. I'm going to write this out as x sub I minus mu squared all over 2 sigma squared. I'm running out of space here, but this is all in the exponent. Okay, so we wrote this out a little differently before in terms of this was minus 1/2 x minus mu over sigma quantity squared. We're just writing it this way because we're going to be starting to break it apart. Okay, so this is our normal distribution here. Okay, that's our probability density function for things that are normally distributed. Okay, let's set up some boundaries here. So my x values are all real numbers, right? My mean values, oops, are all real numbers. And my standard deviation or my variance, my standard deviation is all positive values, okay? All right, so now let's think about our likelihood function. Let's move this over. So our likelihood function is going to be, we're looking for the likelihood of mu and sigma, okay, which is how we're going to set this up. So I'm going to look at thinking about each of my individual x sub i's. So I've got f of x sub 1, and I've got a mu and a sigma squared, that's my variance, times f of x sub 2, mu, sigma squared, so on and so forth, times f of x sub n, mu, sigma squared. Okay, we're going to do a generic one first, and then we're going to take a look at our individual values here with the 10 sample sizes. Okay, so my likelihood function, right, I've got these individual values, I've got my unknown parameter, and I've got my variance. So I'm multiplying these together, so this is our product symbol. Okay, it's like a capital Pi. Our product symbol, I equals 1 to n, right? I'm going to go f of x sub I, mu sigma squared. Okay, so we're going to start plugging in based on our probability density function that we wrote down before. So what this is going to look like is this. So I'm going to go 1 over sigma radical 2 pi e to the minus x1 minus, oops, I should have given myself more space, all over 2 sigma squared times 1 over sigma radical 2 pi e to the minus x2 minus mu squared all over 2 sigma squared times so on and so forth times 1 over sigma radical 2 pi e to the minus x sub n minus mu squared all over 2 sigma squared. Okay. So all I did was expand out this product from I equals 1 to n, right? So I started off x sub 1, x sub 2, x sub 3, x sub 4, x sub whatever, all the way up to x sub n, okay? So I'm plugging in my x sub i's into my probability density function for a normally distributed data set, okay? So this is all of our products. We're going up to n. So now we're going to start bringing things together, right? Let's think about our constant terms. This is our likelihood function now. So my constant terms, right? So if I multiply, let's just call this, we'll call it A. So if I multiply A times A times A times A times A, and I do it n times, right? I'm basically going to get A to the n, okay? So this whole constant term right here, okay, is that constant term raised to the nth power because I'm multiplying it n times. Okay, so let's put this together. So this is going to be 1 over sigma to the n, and I'm going to do it like this, radical 2 pi to the n. That's all there. That's my constant term. Right, now I'm going to do this. I've got this e to the minus 1 over 2 times sigma squared times x minus 1, x sub 1 minus mu sub I squared. Okay, so I have to think about, I have to be a little creative how I'm going to put that exponent together. They all have the same base, so I need to think about how I'm going to do this. So when we have the same base, I have to sum up things, but I've got this constant term that gets, you know, it's in each of these sums. So what I'm going to do is I've got a sum, but I'm going to factor out that constant term. So I'm going to multiply minus 1 over 2 sigma squared times the sum. This is in the exponent, right? So in this sum, I equals 1 to n, right? Because when if I have x to the 1 times x to the 2 times x to the 3 times x to the 4, it's really x to the 1 plus 2 plus 3 plus 4. So we're summing up these exponents. That's what the sum is for right here. Okay, so how am I going to do that? So this is going to be x sub I minus mu squared. Okay, x sub I, because I'm summing up all of those x sub i's, right? And I'm bringing these exponents together. So this is my likelihood function, right, from the product, all these individual products, right? And this is what the likelihood function is. I need to break this apart, right? I've got all this stuff happening in an exponent, so I need to break this apart because I need to be able to sum, to be able to solve for my maximum likelihood estimator. So I have to do, take the logarithm, take the natural log of both sides, take things out of the exponent so that then I can start thinking about how I'm going to maximize it. So I'm going to take the natural log of both sides, right? And then, oops, and what that's going to happen, so natural log of this whole thing, 1 over sigma n radical 2 pi to the n times e to the minus 1/2 sigma squared sum I equals 1 to the n x sub I minus mu squared. I'm taking the natural log, oops, sorry, I'm taking the natural log of this. Okay, when I do this, remember our properties of logs, things that are multiplied together get added, okay? Things that are in the division become subtracted, and things that are in the exponent get brought down out front. Okay, so let's start breaking this apart here. So what this is going to look like is natural log. I'm going to bring this up as a negative exponent. So sigma to the minus n radical 2 pi to the minus n plus natural log, right? This is natural log of this whole thing, e to the minus 1/2 sigma squared sum x sub I minus mu squared, right? Natural log of this, right? Natural log of e is just 1. This comes down out front. So this is like saying, let's see, natural log sigma minus n radical 2 pi minus n. This is going to be, I'm going to bring all this stuff out front here. So this is going to be minus 1 over 2 sigma squared, right? Times the sum x sub I minus mu squared times natural log of e, but natural log of e is just equal to 1, so I'm not going to worry about that. Okay, so now I have to take the derivative, right? And I'm taking this with respect, sorry, you can see that, taking this with respect to the mean because it's, we were told it has an unknown mean. So I'm doing the derivative of our natural log likelihood function, right? But I'm doing it with respect to mu. So now when I take the derivative of this right here, right? So I don't have any, you know, mean values, any mu values here. So this really is just a constant term, okay, because sigma is known. So then this part here goes to 0 because the natural log of something that's just a number, take the derivative of that is equal to 0 minus, I'm going to take the derivative of this whole thing here. So I've got the coefficient 1 over 2 sigma squared. Okay, I've got this, I need to take this derivative of. So when I take the derivative, I'm taking it with respect to mu. So I've got this 2 out front times the sum, and this is I equals 1 to n x sub I minus mu, and I decrease my exponent by 1, right? But now my chain rule says I have to take the derivative of what's inside, which gives me a minus 1. I set that derivative equal to 0. This is a lot of work. I set that derivative equal to 0, and now I'm going to solve for my mean value. Okay, and that's going to give me the maximum likelihood estimator for the mean. Okay, so let's go ahead. This is some algebra here that we're working through. All right, so now I've got 1 over sigma squared by minus 1 over sigma squared sum of mean equals 0, which is 1 over sigma squared x sub I 1 over sigma squared equals 1 to n of mu. All I did was bring it over. I've got these 1 over sigma squareds on both sides, so I can get rid of those, you know, divide those out. So what I'm looking at is y equals y equals 1 to n of mu. okay, which is basically like I'm summing up this constant term mu n times, right? So this is like saying this is n times mu, okay? So what I'm doing, and now I want to be able to divide both sides by n so I can get an estimator for my mean value. So my mu, I'm going to call this mu hat now, is the sum, x by this is I equals 1 to n all over n, which is really just, right, that's just the sum of all of our sample values divides the average, right? So this is in a normal distribution, right? Let's write this down as a little note. In a normal distribution, which is what we were working with, right? Our mu hat is equal to the average or the mean of our samples, right? So sum up of all of my sample values divided by the number of samples that I have, and that's going to give me the maximum likelihood estimator for our mean value, okay? So if we do this, right, let's calculate it out for our particular problem. I'll do this in a different color. Black here. So for our example, right, so I'm going to say for our mu hat, for our example, we've got 10 samples, so 1 over 10. I'm going to sum them all up. So we've got 115 plus 122 plus 130 plus 127 plus 149 plus 160 plus 152 plus 138 plus 149 plus 180. Right, these are all the sample values that we were given. Sum them all up, divide them by 10. I have 10 samples total, and then I find that the mean is equal to 142.2 in my units. Okay. So given what we have, so I wanted to put your attention back when we talked about in example 2, we were dealing with a binomial experiment, a yes-no experiment, and basically our maximum likelihood estimator for P, which is P hat, right, is the number of yeses divided by the total samples, okay? In our normal distribution, okay, our maximum likelihood estimator for the mean is the mean of our samples, right? It's the average of our samples. Okay.
What does the hat value mean on the mu?
The hat is a so it's, so you think about it, it's a calculation, right? So we the hat, or we could have done it as mu sub e. It's basically a way of designating that this is the maximum likelihood estimator for our mean. If we were told our population mean, like we were told in the original problem, we were told that let's see, back at the beginning, we've got American women, they're normally distributed, but we don't know the mean, right? We have the standard deviation sigma, but we don't know the mean, which is, it's academic, right? But meaning that there's no way that we would know what the standard deviation is without the mean, but we're pretending. So we don't know what the mean is, right? And then, so we have to be able to come up with a way to estimate what the population mean is, right? And so we're saying because the population of the, you know, the weights of the population is normally distributed, that means that I can come up with a formula, right, for being able to calculate my maximum likelihood estimator. What's my estimator that's probably has a really high probability of being correct, of being close to what the population mean is. And so this is what we call the method of maximum likelihood, which means that essentially for normally distributed items, I'm going to take the average of the samples, and that's going to give me a really good estimate of what the population average is. So the hat just designates the fact that we weren't given what the population mean was, and I had to come up with an estimate for it. Does that make sense?
Thank you.
Okay. All right. Okay. Whoops. Sorry. Okay. So that was example 3. Does everybody have? Anybody need more time writing it down? No. Okay. Getting into the page. I'll scan this in after class today. All right. So in example 4, what happens? What do we need to do when we have, say, we've got a couple of variables? Like, so the previous 2 examples that we did, I was only missing one of the variables. Like I was missing the probability, or I was missing the mean. But what happens if I'm given a random sample and I don't know the population mean and I don't know the population variance or the standard deviation? So how do I find maximum likelihood estimators, what we call our estimators for two variables. Okay, so this is an example here where I've got these, right, x1, x2, all the way up to xn, and they're random samples, and we're saying that the underlying data is normally distributed, which means when we tell you that normally distributed, we know what the probability density function is. That's the one that we just worked with. We'll write that down. But the problem is we don't know what the mean is. We don't know what the variance is of our overall population. We just have our sample size. So let's work through how we think about what's our process for coming up with estimators, two estimators, right, when we don't know both of these here. Like in the previous examples, we're only missing one of the estimators. Okay, so let's think about it. I'm gonna switch variables a little bit so I can keep track. So I'm gonna call theta 1, I'm gonna call my mean, because that's one of the things I'm looking for, and I'll call theta 2 is my variance. That's my second estimator that I need to find. And then because it's normally distributed, our probability density function for this data, right, is going to look like x is going to look like 1 over, with these variables here, radical sigma 2, radical 2 pi, right? This is our standard deviation, but we're saying that sigma 2 is equal to the variance. So we take radical sigma 2, right, times e to the minus 1 over 2 theta 2 x sub I minus theta 1 squared, right? So all I did, look at what all I did was I replaced the mean with theta 1. I replaced sigma squared with theta 2. Right? Remember in our equation, this is just plain sigma, so we're taking the square root of sigma, sigma squared right there. Because all we did was replace that. And this is actually going to be our function, x sub I, theta 1, theta 2, right? So that would have normally been x sub I, the mean, and the variance, okay? But we've replaced it with our two variables that we're now going to be solving for. And that was just so that we could keep track of like what variable is it that I'm looking at. Okay, so let's set up some range of values for these things here. So my theta 1 is all real numbers, and my theta 2 is all positive numbers. Okay, positive and zero numbers, all positive numbers, sorry. So our likelihood function let's write down. So our likelihood function is kind of like carrying along with what we did before, right? We're going to take the product of all of these things. So now the likelihood function is a function of two variables, theta 1 and theta 2, right? And I'm taking the product, I equals 1 to n. How many samples do I have of my probability distribution? So this is f of x sub I, theta 1, theta 2, right? I'm going to multiply out. These are independent, okay? Each of these samples are independent. And I'm going to be able to multiply out each individual probability function. So let's go ahead and set that up. So that's going to look like 1 over radical theta 2, oops, theta 2 radical 2 pi e to the minus 1 over 2 theta 2 times, this is going to be x1 minus theta 1 squared. That's my first one, times 1 over theta 2 radical 2 pi e to the minus 1 over 2 theta 2, 2, that's a 2, minus theta 1 squared, right? So this is our mean, right? And this is our variance. And this is our x1, this is our x2. And we're going to just keep multiplying all those out until we get to x sub n, 1 over theta 2, radical 2 pi, e to the minus 1/2 theta 2, that theta 2 is in the denominator, x sub n minus theta 1 squared. It's kind of like what we did in the previous example, only now we have theta 1 and theta 2 instead of mean and variance. Okay, so this is our product. Now we're going to start bringing together, right, summing up our exponents like we did in the previous example. Okay, so let's go ahead and do that. So our likelihood function is going to look like this. So 1 over, so I've got radical theta 2, but that radical theta 2 I summed up n times. So I multiplied it by itself n times. Right, this is radical 2 pi. I multiplied that by itself n times, times e to the, right, minus 1 over 2 theta 2. Remember, we're summing up all these exponents. This is a constant term in all of those sums, so I'm going to factor that out and then sum up all those exponents. I could include it in all of my sums, but I'm going to factor it out, times the sum I equals 1 to n, x sub I minus theta 1 squared. Okay. So that's my basically multiplying everything together, right? So when I have a product of things, remember when you have a product of things, you sum the exponents together, right? That's where the
I have a
sum.
question.
Yep.
Where do you keep getting this equation of like 1 over the variance times 2 pi times e to the negative?
That's your equation for the standard normal. Do you remember when we talked about this in, it was in chapter 4.3 when we first introduced the standard normal, the normal distribution curve? We said the probability density function for the normal distribution curve is this. It's 1 over sigma times radical 2 pi times e raised to the 1 over 2 times sigma squared times x bar. We would call it x bar. That would be like our sample mean minus mu quantity squared. That is
Oh,
that's your probability density function for a normally distributed set of data.
okay.
Yeah, when we first
Thank
started
you.
talking about probability density functions, we gave it to you like this is you know, x squared times, you know, 3x plus what, I mean, whatever. We give it to you as a whole function, right? And that was it. Kind of, they were sometimes they were linear, sometimes they were whatever, right? And so now we're saying we're moving into the realm, in the statistics realm, where most of the data is normally distributed. That's our bell-shaped curve. The normal curve, right, looks like this. This is the equation. Okay, this is the equation that you could type into your computer and roll through a bunch of like x values, okay, or your x bar values, and it would plot out a normal curve. Okay, so that this is the actual equation for the probability density function for a normally distributed set of data. Yeah.
Okay, thank you.
That makes sense. Yeah, so like the Poisson has it's set, right? The lambda, you know, raised to a value, you know, e raised to a value divided by something. That is a very particular Poisson curve, right? Our uniform distribution, remember we're talking, the uniform distribution is completely flat, right? Across, you know, some specific value. And so normal distribution has a curve that represents it too. These are standard equations, okay, that you should know in the back of your mind that the normal distribution comes from this equation right here. Okay, so that's where that keeps coming. I'm not pulling that out of thin air. That's actually our normal distribution equation. Okay, so
Okay.
what's that? You're good.
Yeah, thank you.
Okay, all right. So our likelihood function, right? We multiplied all of those normal curves together. We summed up all the exponents, right? And now what we need to do is we have to take the natural log to get things out of the exponents, so then we can take the derivative. So let's take the natural log first. We're going to take the natural log of our likelihood function. Oops, that's a 2. Okay, so first thing we're going to do is we're going to take natural log of both sides, theta 1, theta 2, and that's going to equal to the natural log of this whole thing right here. I'll just write it down. 1 over radical theta 2 to the n, radical 2 pi to the n, times e to the minus 1 over 2 theta 2 times the sum I equals 1 to n, x of I minus theta 1 squared. I'm taking the natural log of that whole thing. Okay, when I do the natural log, it breaks things apart. It makes the math actually, doesn't seem like it, but it makes the math a lot easier because it's going to break all this stuff up so that when I go to take the derivative, it's not a huge mess. Okay, so now when we do this, let's remember our properties of logs, right? So things that are multiplied get added together. So the natural log, I'll just leave this here as 1 over because this is going to become 0 when we take the derivative. I to the n plus natural log of e to the, that's an e, minus 1, oops, sorry, I already did that, 2 theta 2 sum x of I minus theta 1 squared. This is I equals 1 to n. Right, so let's remember, right, exponents get brought down in front of the natural log. Natural log of e is just equal to 1. So this is natural log 1 over radical theta 2 to the n, radical 2 pi to the n. Seems like a lot of work, but it's actually better. Minus 1 over 2 theta 2 times the sum I equals 1 and x of I minus theta 1 squared. And this is times natural log of e. Natural log of e is just equal to 1. Okay. All right. We good so far? I could break this stuff up too. Actually, I'm going to break this stuff up too because we're going to end up taking the derivative of different things. So let me break this part up here, okay, into 2 separate entities because these 2 things are actually being multiplied together, so I can split those apart as well. So this is going to become natural log of radical theta 2 to the, this is going to be why do I have that like that? Plus natural log of radical 2 pi to the n minus 1 over 2 theta 2.
Do we care about the ln 1 over rad theta 2 to the n, that value now because we're taking the derivative with respect to theta 2?
Yeah, that's why I broke it apart. So in the past, like in the previous example, we weren't taking it with respect to the derivative with respect to the sigma squared. So I could just ignore that part because it was going to go to 0. But now we're actually going to take two derivatives, one with respect to theta 1, one with respect to theta 2. And then that's why I broke this apart right here. This part right here, the natural log of 2 pi to the n, we're not going to worry about. That's going to be a constant term, but we're going to need both of these elements because we're going to take derivatives, one with respect to theta 1 and then another one with respect to theta 2. So we're going to need these as we go. All right. Okay, so now
Someone in chat also asked if yeah.
Yeah, then the exponent should be negative. Yes, negative there. Yep, good. Okay. Which is actually, this is like natural log of theta 2 to the minus n over 2 because it's, radical is 1/2 plus natural. I'll just leave this as radical 2 pi to the minus n. And we're going to bring that down because this will be like minus n over 2 natural log. Can you guys even see what I'm doing? Natural log of theta 2, right? I brought down the exponent, okay? Just so we can kind of, when we go to do the derivatives, it'll make sense. Okay, are you guys good with this page? I need to flip the page to have a different paper to work on. Anybody need more time to write this stuff? Okay, good. All right, so let's just write it all out here so we have it in front of us. So we've got the natural log of our theta 1, theta 2 equals minus n over 2 natural log of theta 2 minus n over 2 natural log of 2 pi. This is going to be a constant. I'm not going to worry about it, but I'll just put it in place. Minus 1 over 2 theta 2 times the sum x of I minus theta 1 squared. Okay, so this is our natural log of our likelihood function. Natural log's broken it apart. It's actually, it looks more simple now, right? That I don't have a lot of exponents and a lot of things that are being multiplied or divided out. So when I go to take the derivative, I now have 1, 2, 3 different individual pieces I'm going to take the derivative of. Okay, so now what we're going to do is we're going to take, excuse me, the partial derivatives with respect to theta 1 and then theta 2, right? This is 2. Theta 2, we're going to set each derivative equal to 0 and then solve for theta 1 or theta 2, depending on which one we've taken the derivative according to, okay? All right, so that's our process. That's our next step, okay? So our first thing, right? We're going to take it with respect to theta 1. We'll do that first. I'm going to take the partial derivative, the natural log of our likelihood function, theta 1, theta 2, with respect to theta 1. Okay, so this is my lowercase Greek letter d, right? This is my small delta, so it means I'm taking the partial derivative. So I'm taking this with respect to theta 1. So my first term becomes 0, my second term becomes 0. That was theta 2. These are all constant terms, so I'm taking it with respect to theta 1. Okay, so now minus, I've got this constant term, 1 over 2 theta 2 times, okay, we're going to go, I've got this exponent here, I'm going to bring it down, x of I minus theta 1. I reduce the exponent by 1. I have to take the derivative of what's inside, right? So I take the derivative with respect to theta 1, I'm going to get a minus 1, okay? All right.
Why does the first term go to 0?
It's a theta 2, and I'm taking this with respect to theta 1. So everything that isn't attached to a theta 1 is considered a constant term.
What are
Okay, even though
those? Nope, sorry. What are the symbols at the beginning of the line?
Right here, lowercase
Y-
d, yeah, that means partial derivative. So you know how when
What
we
the
do
heck?
derivative, we do d? Well, this
Yeah.
is our symbol for partial derivative.
Huh.
It's like a delta.
Okay. Okay. I'm not
Okay.
really sure what those are, so I'm kind of confused.
Yeah, it's a lowercase d in the Greek letter alphabet, and it stands for a partial derivative.
Okay.
Okay. All right, so let's go ahead. So this is I equals 1 to n. We're summing that up. Okay, so let's go ahead and put this together. So this is going to be 1 over theta 2. That's our constant term times the sum from I equals 1 to n, x sub I minus theta 1. And I'm going to set that equal to 0. Okay, so I'm going to now distribute the sum to both terms. So this is going to be 1 over theta 2 times the sum of x sub I minus
Do we
1.
keep that theta 2 because it's attached to a theta 1?
Exactly. It's like it's like as though this were just a number, right? So like 2x squared, right? And I go to take the derivative, the 2 is still there, right? So the 2 times the exponent 2 times x. So it'd be 2 times 2 times x. So it's just a coefficient at this point.
Okay.
Okay. So theta 2, sigma theta 1 equals 0. Okay. And then I'm gonna go there equals right, this is, right, we're summing this up, I equals 1 to n, right? I can get rid of my theta 2's because I have them on both sides of the equation, okay? I'm basically summing up theta 1 n times, which is the same thing as saying I'm multiplying theta 1 by n. Oops, that's a 1. Theta 1 by n, okay? So now I want to be able to solve for theta 1. So I'm going to divide by n. So now it becomes theta 1 becomes a hat because this is our answer. It's an estimator for theta 1 for our mean. Okay, so this is our I equals 1 to n, x sub I all over n, which is our, right, our maximum likelihood estimator for our mean. We called it, we switched variables just so we could keep track of things, okay, which is really just the average of all of our x values, right, which is what we said before when we were looking at our normal distribution, right? So our mu hat, okay, which we call theta 1 hat, our mu hat, we're summing up all of our sample values, x sub i's, and we're dividing them by the total number of x sub i's that we have. We're taking an average of all of our sample values. Okay, that's what our maximum likelihood estimator for our mean is. Okay, so I'm going to scroll up a little bit and we'll start doing the second partial derivative, which is with respect to theta 2. So I'm going to take this partial derivative of our likelihood estimator with respect to theta 2. Okay. So now we're going to do this. So now I'm back up here. I'm looking at this equation here. Okay. So now I'm looking at things that are attached to theta 2. So this is still a constant term. Now this becomes a constant term to this because theta 2 is the thing that I'm taking my derivative with respect to. Okay, so keep that in mind when we start writing out what our derivative is. Okay, so now this is going to be minus n over 2. This was times 1 over theta 2 because we had the natural log of theta 2. So the derivative of the natural log, okay, minus 0. This is going to be minus 1 over 2 times the sum x sub I minus theta 1 squared. That's our coefficient, right? Times minus 1 times, oh, I'm running out of space, theta 2 to the minus 2 power. Oops. So if I can, this is right here, this is theta 2 to the minus 2 power. I ran out of space. That's what that says right there. Now, why is that? Because we had 1 over theta 2, taking the derivative of that, right? So it's basically theta 2 to the minus 1. So that's where the minus 1 comes from, right? And then I have to decrease my exponent of theta 2 by 1. So I get minus 1 as my chain rule, and then minus 2 is my new exponent. Okay. All right. Let's start working through. Let's start cleaning it up. So this is going to be equal to minus n over 2 theta 2 plus 1 over 2 theta 2 squared times the sum x sub I minus theta 1 squared equals 0. I have to set that equal to 0. Okay, I have to maximize it. Okay, so this is going to equal to n 2 theta 2 equals 1 over 2 theta 2 squared times the sum of I minus theta 1 squared. Okay, so I'm going to multiply, to try to get rid of things. And then I'm going to, so kind of clean it up, just do some algebra here. So I'm going to get n theta 2 equals the sum, I equals 1 to n, x sub I minus theta 1 squared. Okay, I want to divide by n. So we're going to get theta 2 hat, right? This is now our estimator. Theta 2 hat equals the sum, I equals 1 to n, x sub I minus theta 1 squared divided by n, okay, which is equal to sigma squared estimator. Which is consistent with what we were thinking of when we were calculating out our variance in the past, our formula for how we calculate out our variance. We take each individual value, we subtract it from the mean, we square it, we sum those up, and we divide it by the total quantity that we have. And that's going to give us our variance. Okay. These are our partial derivatives, one with respect to theta 1, one with respect to theta 2. So it's just a method for working through when you have multiple variables that you need to solve for, multiple unknown variables. Okay. Your logarithmic differentiation is going to help you a lot because ironically, it cleans things up and makes it easier, right? It makes your function much easier to take a derivative of, because ultimately, right, you want to take the derivative, set it equal to 0, and having it in logarithmic form just means that you've broken things apart in your original equation. Okay. And that's the end of chapter 5.2, which is the method of maximum likelihood.
I have
You
a
don't-
question.
Mhm.
So for both of the equations or that we found, does it assume that you have to know theta 1 and in the for theta 2 hat?
Well, no, so theta 1 and theta 2 are the unknown variables. Those are the ones that we are trying to find estimators for, right? So theta 1 represents our mean, and theta 2 represents our variance, right? All we did was switch variables so that it would be easier to keep track. Okay, I didn't have to. I could have just left each of these as mu and sigma squared, and then done the partial derivative with respect to sigma squared. Sometimes it's easier to switch variables so that it kind of cleans up the equation and you can see it, you know, a little more easily about like what's an unknown variable and what's not. So in this particular case, we had two unknown variables. I didn't know what the mean was, and I didn't know what the variance was. This is more likely, right? So you're gathering data, right? You're getting all these samples. This X sub I are your sample data, right? You run an experiment, you have all these sample data, but you don't know what the population mean and the population variance are. Okay, so you need to have a method for being able to figure out what's the most likely mean and what's the most likely variance for my population data. And when we're dealing with things that are normally distributed, it's pretty likely that you're dealing with the actual, you can take a look at your sample size, right? And then use your sample size to come up with estimators for your mean and your variance of your population. That's what this is saying here. Same thing's true for our binomial, right? For the discrete cases too. It's the proportion, right? Proportion of success is divided by the total number of samples. Those are our estimators for our mean, okay? Or in the case of the binomial, for the probability P. Okay.
So even though we found sigma squared hat, even though we use theta 1, which is like mu in this case, we still don't know it because we're still trying to find it. And then we found it using the partial derivative in the first half.
Yeah, so you're saying like how do I actually get actual numbers out of here? Yeah, so I would say in this case, if you actually had like values for x sub 1, x sub 2, x sub 3, say you actually had values for those, then what you could do is I would solve first for the mu, right? For the mu hat, right? Come up with an estimate for sigma 1, theta 1, and then I could plug theta 1 in here to come up with an estimate for my sigma squared, my theta 2 hat. Yeah, right, because it's this part here, this is now coefficient, but our calculation of variance depends on the distance each value has from the mean, so I need to know what the mean is, right? But the mean here, our estimate for the mean is just based on the average of our samples. So calculate the mean first, take that value, plug it into here, then you can calculate your sigma. Okay. This example here is, we don't actually have values that we're working with, we're just looking at if we just have two unknown variables, how do we calculate what their estimates are? So the two unknown variables are the two most common variables, the ones that you really want to know, which is the mean and the variance for like a population of data that you're trying to gather. The hat just
thank
means,
you.
The hat just means it's an estimate, right? It's a way of acknowledging that we don't really know what the population mean and the population variance are. And that's often the case, right? I mean, you, as researchers, or as you know, you're going to go out in the world, you're going to gather data, okay, whatever kind of data, whether it's, you know, a drug trial, you're going to gather, you know, stress fractures on a bridge, you're going to gather all sorts of data about whatever it is that you're doing. And you're going to be accumulating that data. You don't know what the population mean or the variance are. So you need to come up with, you know, estimates for the population mean and the population variance. That's what this is. Okay, it's a way of acknowledging that we don't have the population data, but we have, based on the samples that we have a pretty good estimate of what we think the population mean is and the population variance is. In chapter 5.3, we're going to start talking about, it's called like basically confidence interval. You guys may have heard that in the news where they talk about this is our data, this is the 95% confidence interval around the data. So we're going to talk about how we start calculating that. And one of the ways that you think about a confidence interval is, I have a bunch of data. I don't know what the population mean is, but I have a 95% confidence that the data that I gathered, you know, is around my population mean. Okay, so that's kind of how you want to be starting to think about what we're doing here, because ultimately in real life we don't really know what the population is, right? That's what we're trying to extrapolate based on all of our experiments. So I gather a bunch of data on a small sample size. Small, the numbers could be really large, but it's nowhere near the population size, right? I can't go out, it's not reasonable to go out into the world and poll 7.5 billion people and make a statement about it. I can't do that. So I'm going to pull some small subset of people and then I'm going to extrapolate out to the larger population. So that's what this is here. We're moving into the realm of more unknowns, and we're going to start talking about, I have confidence, 95% confidence that this is true, or 99% confidence that this is true, or you get the idea. We're going to start working into more statistics, okay, which is the absolute numbers are unknown, and we're talking about what's our confidence in the range of values. Okay. So estimates, right? Maximum likelihood estimate is a way of coming up with an estimator for, you know, given probability density function. We looked at binomial, we looked at normally distributed, okay? But say you had some function, some other probability density function that was like 1 over x squared, say for example, and that was your probability density function. And then x was defined within a couple of values, you know, to make sure that that was going to be a valid PDF. And then given that probability density function, what would be your maximum likelihood estimator for the mean and for the variance? Now you would go through the same method, right? Except that instead of multiplying through our normal distribution values, I'd be multiplying through 1 over x1 squared times 1 over x2 squared times 1 over x3 squared times so on and so forth, all the way up to 1 over x of n squared, right? And then I need to come up with a maximum likelihood based on that probability density function. Okay, we're focusing on the normal distribution and the binomial distributions because those are the most common in the real world, okay? But the method of doing it is the same. These are independent, so I'm just going to be multiplying each individual probability density function with that x sub I in place, okay? Big picture. How's everybody doing with that? Yes, the test is 4.2 through, no, the test is 3.5 through 5.2. Someone's asking on the chat, like what the test covers. This is 3.5 through 5.2. So it's everything that we've done since the last test. Okay, so the last test covered up to 3.4. Now we're picking up where the last test left off. So 3.5 all the way up to the stuff that we just did right now, 5.2, okay, that we just finished up. Okay.
I have a question.
Yeah, what's up?
Can you explain what the central limit theorem is again?
Yes. So the central limit theorem, there's a couple aspects to it. So the central limit theorem basically says, right, if I have like an underlying experiment that's binomial in nature, where I'm asking people, you know, do you believe in this? Yes or no? Does this drug work effectively? Yes or no, right? And so we're looking at yes or no answer. So it's a binomial experiment in the background. As n gets larger, okay, what happens is our discrete data naturally form into a normal distribution. Okay, so the central limit theorem means that as n gets large, our data shifts into, even though it's discrete, our data shifts into a normal distribution curve. And so you may or may not have to do a continuity correction on things with the central limit theorem. But the central limit theorem is like a curve fitting of a continuous distribution function, right? Or that's our normal, that's one over sigma times radical 2 pi times e to the minus that whole thing. This is our probability density function for our normal curve. It's a curve fitting of a continuous probability density function on top of discrete data. Okay, so depending on the values of n, like the numbers of n that you have, you may have to do a continuity correction, which is like saying, I've got a discrete data set in the underlying background, but I'm curve fitting a continuous function on top of it, so I have to accommodate that. So I may need to add or subtract 0.5 in order to get the correct data set on there. Like some of the examples that we did at the beginning of 4.3, right, where we were talking about continuity correction, right? And that's where you would be thinking about our central limit theorem, which is we're looking at data naturally sifts into a normal distribution pattern, okay? And then I need to kind of adjust for that. As n gets really large, then oftentimes, you know, you may or may not need to actually worry about the central limit theorem.
Okay, thank you.
Yeah, sure.
I had a question about the dice problem in the 4.3 homework, number 16. It was just like asking,
Yes, so can I just want you to hold your thought. So I'm more than happy to talk about the homework. Can you come to office hours and then we can go over homework problems in office hours? Because
yeah, it was just a question about the z function though. Like, mu equals np in the z to find the z value, but if you have like in that, for example, that dice problem, there's 100 dice. So would you multiply that mu by 100 when you're trying to calculate for z?
So 4.3. So you want me to answer a homework problem when I really want to actually go over the homework problems in office hours? I'll answer this really quick.
No, yeah, I can wait till office hours too.
If you can wait, that'd be great, because then we can actually spend time, you know, working
Okay.
through it, and then I can discuss it. And it's,
Yeah.
and I don't mean to cut you off, but you know, this summer schedule is really tight, and I need to start 5.3, even though 5.3 is not on our test. We actually need to cover it today so that we don't fall behind in terms of things. The lecture examples for 5.2 I'm going to put up online this afternoon. I'll scan it in and put it up. I'm also start looking into our homework solutions. I posted some homework solutions yesterday from last week's homework. Later this afternoon, I'll post some homework solutions for things that are due today. I hesitate to, I don't want to, you know, do it too early, because I actually want you guys to work it through and try out the homework examples. But I will put the solutions up at some point, you know, late this afternoon, or, you know, early evening for this week's homework. So you can have that to check your answers against things, so that when you take the test, you'll have the correct answers on your homework stuff. Okay. All right. So let's switch gears to 5.3. And then 5.3 is not going to be on the test, but it is something that we need to make a start on. So 5.3, make sure you guys have the 5.3 lecture example page. I'm going to start working on things like that today. All right, so 5.3, we were talking about confidence intervals before, where we don't know what the population mean is, and we want to be able to talk about confidence intervals. So this is chapter 5.3 is called interval estimation. Okay, so we're going to talk about confidence intervals, right? And then we're also going to use it to help us start doing statistics with confidence intervals in a way of being able to describe bounds on our mean or our proportion values. Okay, so let's think about what's our problem that we have when we do experiments in the real world. So the problem is that we have like point estimates, right, which is what we were doing in the last chapter. So the maximum likelihood method is a point estimate. Point estimates such as our sample proportion, which is our p hat. Okay, so that was the p hat example that was based on our discrete values. Sample proportion or sample mean, which is our mu hat. Okay, or our sample variance, which is our sigma squared hat. These are all things that we just calculated in the previous chapter section, right? So all these things here, they all depend on the sample that's been selected, right? So I'm coming up with, based on the samples that I have, I'm going to come up with an estimate for my, population proportion, my sample mean, my sample variance. And so, I need to have like a broader way of describing the overall population. So if we want to know the population values, I guess that's the ultimate point of statistics, is to take a sample and extrapolate it out to a broader population. So we want to know the population values, which is our mean, our variance, our proportion, right, etc., whatever those population values that we're looking for. And and we need to know how close our estimate is right, these sample estimates, how close our estimate is to the actual population value. Right, so I had, like in the previous chapter, right, we had all these samples, and we said, well, what's our maximum likelihood estimator for the mean, the population mean? So I did my sample mean, right? It was normally distributed, did my sample mean, but I don't know, like how close is that sample mean to the overall population mean? So our interval, our confidence intervals are going to help us come up with a level of confidence to tell us how close our estimate is to the actual population values, because ultimately we want to be able to make inferences about the overall population. So that's our problem. Our solution is going to be to use what's called a confidence interval. And we hear this talked about a lot, right? And in the news, when people do statistics, they say, here's the line of data for all these different things. Here's the 95% confidence interval around that data. Okay, so we're going to start learning how we do that. So let's talk about what is it. So confidence interval is an interval. It's really just a range of values that we can be confident within some percentage. I can be confident within some value, within some percentage value, confident that it contains the actual parameter. This is our unknown parameter. Okay, so we would say things like, I've got an unknown mean value, right? And so I'm going to come up with a 95% confidence interval around that mean value. Okay, so I'm going to say, I don't know what the population mean is, but I'm 95% confident that it's within this range of values here. So it's also, a confidence interval is a way to quantify the amount of uncertainty in an estimator. Okay, so we've come up with a maximum likelihood estimate for the mean, and then I've got this 95% confidence interval. Does that contain the mean or not? Or I can say this is, I'm 95% confident that this sample estimate, contains our population mean. We can also look at the width of the confidence interval to get a sense of the precision right? So if our width is really wide, right, then maybe I don't have as much confidence in my estimate. If my width is really, really narrow, I've really narrowed down, if I say I'm 99% confident that my mean is within this interval here, that's a pretty high confidence of things, right? But if I say, I don't know, about 50% confidence, it's a pretty wide interval of values that's maybe going to contain that mean. Okay, so it's a way for us to be able to look at something and say, okay, this is a reasonable estimate or not. Okay, so we need to have, you know, lower, the way we represent our confidence interval is that we have lower and upper bounds. On our confidence interval. Right, so I say I've got my lower bound, which is, say, you know, I'm looking at my mean mostly is what we look at, and my upper bound, right? So my lower bound of values, my mean is between my lower bound and my upper bound. So how we calculate our lower bound and our upper bound is what we're going to be talking about, you know, today. So we have what's also called a confidence coefficient. Okay, so confidence coefficient is a way for us to, we're going to use our Z table. It's a way for us to be able to say, you know, if I'm 99% confident or 90% confident, or 95% confident, right? So my confidence coefficient is 1 minus alpha, right? So let's do it like this. If I say I've got a 95% confidence interval, right? I'm going to convert this into 0.95. Okay, so 95%, right, is my confidence. So my alpha is how we specify things. So this is equal to 1 minus alpha. Okay, so if I were to subtract out 0.95 from 1, I'm going to get my alpha is equal to 0.05. Okay, so we'll often say things like, if we say I want a 95% confidence interval, I'm going to use an alpha value of 0.05, right? Because I calculate that from my 95% confident. Or I can say, do the confidence interval at the alpha equals 0.05 level. Okay, that means it's a 95% confidence. Okay, so we think about our confidence coefficient in terms of 1 minus alpha, but alpha is the metric that we actually use to multiply things out. Okay, and so yeah, so we'll just write down the confidence level. Right, it's going to be 1 minus alpha times 100%, right? So that's where we got the 95%. So 1 minus 0.05, you know, times 100% is going to give us 95% confidence. Okay, so you guys have all this? I'm going to turn the page. Okay, so typical values for our confidence intervals. Okay, so most typically we see 95%, right, is our typical value. And that's usually like what would be 0.95. 99% is a really tight range of values. It would be 0.99 is the value that we'd be working with. Also, sometimes you'll see 90%. Okay, when I'm kind of confident, but not quite, you know, so this would be 0.9. The higher the number, right, so 95, 99 means I'm more confident, right? So I'm getting more confident the higher the number. I wrote these out of order. This is less confident the lower the number. And all that means is that my interval is wider, right? So if I'm at a 99%, my interval is really narrow. 95%, my interval is a little bit bigger. 90% is even bigger. 50% is really big, right? So this just tells us basically how wide our interval is, okay? So how do we calculate these things? So what I'm going to do is we're going to go back to our Z values, right? So we're going to think about our like a Z interval of things, right? And we're going to take a look at stuff around the mean. Because typically, you know, like we said in the previous example, right, I can't calculate my variance without knowing what the mean is, right? So oftentimes we're talking about what's our mean value and what's a confidence interval around that mean. So we're talking about a Z interval now around our mean. So think about when we do our Z values, right? On my standard normal curve, okay, things are centered at 0. This is my standard normal. So I've got a positive Z value and a negative Z value, okay? But now what happens is, because we're talking about 0.95, right? Say, for example, I need to, what's left over, like what's in between here and here is my 1 minus alpha. Right, so let me shade this in here as, this is my confidence interval right here. My 1 minus alpha is my confidence interval. So this is like my 95% confidence interval. what's left over is alpha divided by 2, right? Right, so if the whole thing, my confidence interval is 95%, I have 0.05 left over, right? But it's two-tailed, so I've got a little bit, I've got half because it's symmetrical. 0.05 divided by 2, 0.05 divided by 2. Okay, so it's alpha over 2. So when we think about our z values, we think in terms of z alpha over 2. Okay, so so I've got my z table. Now the alpha in the 95, these things are probabilities, right? So I'm kind of doing a reverse lookup on my z table. So I look over here and I'm looking for 0.95. Say for example 0.95 or 0.05, 0.025. So I'm looking over here 0.95. Where am I going here? Let's see. Right, I want to get as close as I possibly can, right? It's my 0.95, right? And my 0.025 is my alpha that I'm looking for. So, right, the 0.95 is going to be here, but my, let's do this. This is my, I'm cutting it in half. So remember, our z values are the areas under the curve that are less than or equal to z. So this is going to be equal to, if this is 0.95, I'm going to be looking up z, let's go this, 95%. My alpha equals 0.05. My alpha over 2 is equal to 0.025, right? So this is z equals 0.025. So I have to look up 0.025 on my table here to find out what my, let's see, where am I gonna go? Right here, right? So 0.025, that corresponds to a z value of minus 1.96. Okay, so it's the z values that I'm looking for. So z of 0.025 is equal to minus 1.96, for example. But because of symmetry, right, I've got minus 1.96 and then positive 1.96 because I've split that into two pieces. Okay, I've got a 0.025 here and a 0.025 here. So that's how I'm looking for things, okay? These are probabilities, areas under the curve. Okay, so the 95% confidence, change that into 0.95, subtract that from 1 to get alpha, divide that by 2 to get alpha over 2 because I've split that alpha into two equal pieces, okay? Look up that 0.025 or whatever that alpha over 2 value is on my probability table here to find the corresponding z value that associates with that. That z value that I found based on that alpha over 2 is what I'm going to use in my equations to multiply things. Okay, so let's write down some of what we're trying to do. So this is z alpha over 2, okay, that we're working with. So we're looking at the probability that z is greater than z alpha over 2, and that's alpha over 2, and the probability that z is less than z alpha over 2 is equal to alpha over 2. This is to the right, and this is to the left of z positive z, left of negative z. Okay, that's just kind of putting in words what we did here with our graph. Okay, so we're going to use this to help us define our confidence interval. And this is from my standard normal, my z table. Okay, all right. So let's start deriving what our confidence interval looks like. Okay, so my confidence interval. So I'm going to make some assumptions first. So the first thing I'm going to assume is I've got x1, x2, x of n. These are random samples. And we're going to assume that these are coming from a normal distribution. It's reasonable to assume that until things don't work, but it's very reasonable to assume that because most data sift into a normal distribution naturally, but we need to state our assumptions. I'm assuming these are coming from a normal distribution. These have a mean, mu, and variance, sigma squared, okay? So that means I think about my x bar as being normally distributed with mean and variance, okay? And that means I can say my z value is equal to x bar minus mu all over sigma divided by radical n. And this is our standard normal, okay? Remember to make this adjustment sigma over radical n, okay? So we're also going to make an assumption that the population variance is known. Sigma squared is known. We're going to come back to this for cases where it's unknown, but right now we're going to assume that the population variance is known. Okay, then I can state that my 1 minus alpha 100%, this is my 95 or 99% confidence interval. For the mean, which is mostly what we're looking for our mean, is going to be equal to, I'm going to say it's x bar plus or minus my z value at the alpha over 2 level times sigma over radical n. Okay, this is our z interval for the mean. So we would say it looks like x minus z alpha over 2 sigma radical n, comma x plus, that's x bar, alpha over 2 times sigma radical n. So, right, we have 95% confidence, 99%, whatever our confidence interval is, that's represented by our z value, times sigma over n. That x bar plus or minus that z value, this is going to give us the confidence interval for our mean. We're going to say our mean, we're 95% confident that our population mean is within this range of values based on my sample size. Okay, so this is what we call our z interval, interval for the mean. Because we're using our z value for it. This is what you want to remember here. And all I did was, instead of plus or minus, I wrote it as an interval value. These are equivalent statements here. I'm going to take a minute to show you where this comes from. Okay, this is the equation that you're going to be using, that you want to know. But I just want you to know where this all thing comes from so that you can not think I'm just pulling it out of thin air. Okay, does everybody have this here before I start writing into other stuff? Anybody need more time to write this down? So this is the thing that you want. This is the thing that you would put onto your formula sheet once we start having formula sheets that you can start aggregating things. Okay, so this is the important bit. Okay, so let's talk about where that comes from. Okay, you don't need to do this every time that you're trying to calculate out an interval value. You're just going to use that equation when you calculate it out. But I just want you to see where this stuff comes from. All right, so remember, we're talking about probabilities, right? So I've got minus z alpha over 2 is less than or equal to z, which is less than or equal to z alpha over 2. So, and that is equal to, right, 1 minus alpha. So that's like saying, right, the probability that things are within our 1 minus alpha zone is between, this is, I'll call this z alpha over 2, z alpha over 2 right here. Okay, that's from that graph that we just put up on the board. So that's what we're writing in terms of probabilities. That's equal to like our 95, that'll be 0.995 for a 95% confidence interval. Okay, and remember our z is equal to x bar minus mu over sigma over radical n. Give me just a second. Okay, so now we're going to start deriving this out. Okay, so I'm going to substitute this z into here. Okay, so I'm going to go the probability minus z alpha over 2 is less than or equal to, I'm plugging this in for my z, which is less than or equal to z alpha over 2, and that's 1 minus alpha. Okay, so now I'm going to take this, I'm going to take this and work it out, and then we'll put it back into the probabilities later. Okay, so just know that all the rest of the work that I do is all this stuff that's inside of our probability equation here. Okay, so let's write this out. So minus z alpha over 2 x bar minus mu all over sigma over radical n z alpha over 2. So I just wrote that out. So now what I want to do is I want to multiply, right? Because I want to get this in terms of, I want to solve this in terms of mu, because I want a mu is greater than this value is less than that value. I want to come up with a range of values for mu. So I'm going to multiply all this out. So I'm going to get minus z alpha over 2 times sigma over radical n is less than or equal to x bar minus mu. It's a minus less than or equal to z alpha over 2 sigma radical n. Okay. And now what I need to do is I have to subtract out my x bar from both sides, right? So I'm going to subtract them here because I'm solving for mu. Mu is my population mean is my goal. Okay. So I'm going to subtract out x bar from both. So I'm going to get minus x bar minus z alpha over 2 sigma over radical n minus mu minus x bar plus, oops, sorry, z alpha over 2 sigma over radical n. Okay, now I got to get rid of this negative, so I'm going to multiply the negative. Remember, signs are going to flip all across the board here. Okay, so I'm going to we'll divide by -1 all across on here. So what's going to happen is this, right? And then I need to do this, and I need to flip my greater than and less than signs. Okay, so this is going to become x bar minus z alpha over 2 sigma over radical n is less than or equal to mu, which is less than x bar plus z alpha over 2 sigma, oops, sorry, that's a radical n there. Okay, now all of this, remember, was inside of our probability statement. Okay, so let's put that back into our probability statement. So the probability x bar plus z alpha over 2 sigma radical n there is equal to 1 minus alpha. Okay, so all we're doing is we're saying the probability that our population mean value is between x bar minus z alpha over 2 sigma times radical n and x bar plus z alpha over 2 sigma over radical n, and that's equal to 0.95, 0.99, whatever. Okay, so this is our statement, right? That's how we get to here. So we say our 95% confidence interval or 99% confidence or whatever confidence interval for our mean is x bar plus or minus z alpha. It's symmetric, so z alpha over 2, this z value is the same, sigma over radical n. Okay, this gives us our interval for our mean values, right? With 95% confidence or 99% confidence or 90 or whatever your confidence interval is. Okay, so we can write this in words. So we'll say we are 1 minus alpha 100% confident that the population mean is within the interval x bar minus z alpha over 2 sigma over radical n to x bar plus z alpha over 2 sigma over radical n. There. Okay, that's what we've just done. This right here or this right here, that's what you need to know. Okay, in terms of answering questions for whatever percent confidence interval that you're looking for. Okay, this is just how we got there and where it comes from. We didn't just pull it out of thin air. It actually comes from our z values. It comes from our probabilities. That's why we can use our probability table, right, to be able to look up what z value to use. Okay, it's different. When we first learned about our normal distribution, we had a z value. We calculated our z value. We used that z value to find the probability. Now I'm looking up my probability. This is alpha over 2, and I'm looking for a corresponding z value. That z value I'm going to put into here. Okay, it doesn't matter if you have a z value that's positive or negative on your table. Okay, because it's going to be both positive and negative. We're going to it's symmetric, so we're going to use both sides of it. Okay. All right, so let's do this. We'll work through one example first on 5.3, and then we'll stop, and then we'll continue it on a Monday. All right, so my 5.3. So I'm looking at my 5.3 lecture examples. Example 1. So we have, sorry there, a random sample of n equals 126 road workers in some major city is tested for blood lead levels. And that's often because the people who work on the roads are exposed to lead from exhaust. And so they want to, maybe people want to test to see if their blood lead levels of the road workers is higher than the general population. Because if it is, then that would be the basis for like a lawsuit, say for example. So the random samples had a mean of 29.2 milligrams per micrograms per deciliter of blood lead. We're going to assume X, our random variable, is the blood lead level of a randomly selected worker, okay, and that's normally distributed, okay, with standard deviation of 7.5 micrograms per deciliter. People with no exposure to the pollution have an average blood level of 18.2 micrograms per deciliter. It already looks big, especially given the standard deviation, okay? And remember how we said we're assuming in this case here that we know what the population standard deviation is. As we progress along, we're going to talk about what if we don't know what that is. We'll deal with that when we get there. Is there statistically convincing evidence that the road workers have elevated lead levels? Okay, so what we're going to do is we're going to calculate. We're going to use our confidence interval to calculate this. They don't tell us, you know, how to do this, so we're going to state it. So we're going to calculate the 95% confidence interval for the population mean.
Are we always going to just calculate 95%, or will it tell us like 90% or
Yeah.
99%?
Right, exactly. So that's a great question. So most of the examples that we do, we're going to tell you do 95%, 99 or 90 or whatever. We're going to tell you what the confidence interval is. If you aren't told, pick a percent. 95 is your standard confidence interval level. You won't go wrong with the 95% confidence, the most common one. And we'll talk about why that is as we go along and what that actually means. But for now, if you're not told, just pick 95. It's your standard level that you can use. All right, so we're going to do this 95% confidence interval for the population. I could have easily done 99% or 90 or 50%, but 95 is the most common one. Okay, so 95% confidence, right? This corresponds to 0.95, which is my 1 minus alpha. Okay, so I need to solve for my alpha. So my alpha is equal to 0.05, okay, which means that my alpha over 2 is 0.025. Okay, so I have to look up at my z table for 0.025. We did this just before. It's equal to 1.96. Okay, you kind of want to start, you know, getting in the habit of thinking about these numbers. The z for, you know, the 95% confidence is 1.96. It's when they say, oh, it's 2 standard deviations from the mean, it's really not 2. It's 1.96 standard deviations from the mean, but that's okay. It's we're going to use this z as 1.96. So now keep that in mind. Okay, so now let's think about what that means. I'm just going to graph it out. You don't have to graph it out each time, but I want you to be able to visualize. So we've got a normally distributed data. I'm just going to write already in pencil. So our workers, our road workers, have an average blood level of 29.2. And we're looking for a 95% confidence interval around that value, right? So my z value, z of alpha over 2, is equal to 1.96 on this side, and my negative z alpha over 2 is minus 1.96. It's symmetry, right? So it's positive on the larger side, on the to the right of my mean, and negative to the left of my mean. Okay, so right here, this area here, this whole area here is 0.95, right? The area under that curve between these two z values is equal to 0.95, which means that the area here is 0.025 and the area here is 0.025. Just graphing it out just so you can see like what we're trying to do, okay? So you can have a visual for it. All right, so let's start taking notes. So my x bar, my sample mean, we said was 29.2. Okay, I'm not going to write units at this point. My n is equal to 126, and my population standard deviation is 7.5, okay? And we said our z alpha over 2 is equal to 1.96. So these are all the pieces of the puzzle that I need for my 95% confidence interval. Okay, so my 95% confidence interval, I'm going to take my x bar, so 29.2. I'm going to subtract my z value, 1.96, times my standard deviation, 7.5, all over radical 126. And comma, so my mean, I think, is going to be 29.2 plus 1.96 times 7.5. Watch out for your order of operations on your calculator. Okay. So when I do this all out, I'm going to get my confidence interval is 27.89 to 30.51. This is my confidence interval around my population mean. It goes from roughly 27 to 30 or 28 to 31. You can kind of think about it like that. This confidence interval, I'm going to say, this confidence interval does not contain our non-road worker population, right? Does not contain, what was it, 18.2, right? This is our non-road worker blood level. Okay, which means that maybe there's a basis for a lawsuit, right? That means that I can say with 95% confidence that the mean of the road workers, their blood level is significantly higher than the mean of the non-road workers, the blood lead levels. Okay, so that means that if the road workers wanted to take this to court, they would have statistical evidence to say their blood lead levels are significantly higher than the general population, the population of people who don't work in the road. So therefore they need compensation to deal with all the health effects of having, you know, higher elevated blood lead levels. Okay, so we can show, therefore, we can say, therefore, that the pollution contributes, pollution from their job, pollution contributes to elevated blood lead levels. Okay, we're gonna, as we progress along in the statistics portion, we're going to use confidence intervals to help us make decisions about hypotheses, right? So at the 95% confidence level, I can make this statement that these populations, road workers and non-road workers, are significantly different, okay? We're going to use confidence intervals. We're going to use other methods as well. So we're starting to get into the statistics portion of the class, okay? All right, so I'm going to quit here with that example, and then on Monday we'll pick up with the rest of the chapter, and then we'll progress on to 5.4 after that.
I have a question really fast
Yeah.
about this. For the X bar
Mhm.
in the problem,
Mhm.
how do we know which mean we're talking about? Because we're given two.
Yep. So the X bar, so we're looking at, look at what the question says. That's a great question. So the question says we have a random sample of road workers, right? So X bar is your sample mean, okay? So that's the road worker mean, right? So the X bar is this, the 18.2 is the population that we're comparing it with. We're saying that non-road workers have this average value over there. And so that mean, the 18.2 is not in our confidence level, a confidence interval for our road workers, right? We just calculated out the population for road workers, you know, has a 95% confidence that, you know, our population mean is like around between 28 and 31, say, for example. This 18.2 is just something that we're comparing it with, right? So the sample of road workers, the road workers, right? So this, assume X is the blood lead, this is like X sub I, is the blood lead level of a randomly selected road worker. So it's normally distributed, has a standard deviation, okay? So we're looking at X bar, all these X's correspond to our sample set, which is our road worker set.
Okay, so the X bar is basically like the mean.
It's the average of your samples, that's right.
Yeah,
Yep.
okay.
And then we're
All right,
saying
thank you.
we have the average of the samples. So now we want to know, based on the average of the samples, like there are more than 126 road workers all across the country, right? And there are more even in some major city. There, whatever. Like if this is New York City, say for example, there are more than 126 road workers. There's maybe like, you know, thousands, right? But I can't go out and poll all 1,000 of them, or, you know, 10,000 of them, or whatever. I have to take a random sample of 126 of them. Maybe I take that sample from all over, or I just focus on the people in Manhattan instead of, you know, other boroughs. So because it's not reasonable, it's often not reasonable to gather information on the whole population. I have to just do it from a sample set. So I'm looking at a sample of road workers. So the X bar is my sample average, right? And I'm looking for the population mean, the population of road workers, right? So what's the mean of all of the road workers? Somebody somewhere else said we've got, you know, a population estimate for non-road workers, and that's what the 18.2 is. So that's what we're comparing it with.
Okay, thank you.
Sure. Okay, guys, so that's part of 5.3. We'll come back to 5.3 on Monday. If you have questions about things for the upcoming test, please come to office hours today at 12:30, and then we can work through problems. I would say we can talk about things from the test review. Probably your best bet are to look at things like the homework problems. Those will really help, examine, your knowledge of things. So if you have questions on the homework, please come to the office hours, and then you can listen in, come for the whole thing, because I'm sure, other people may ask questions that, will make you think about the answers to things too. Okay. All right, you guys. Good luck. And if I don't see you in office hours, then have a great weekend.
Thank you.
Okay, bye, guys.